So some of the things in the lecture 2 were discussed as part of a previous study group session. So we'll quickly walk through the slides. So we discussed about Skipgram last week. Skipgram is one of the algorithm of word2vec, where given a center word, we try to predict the words around it, the context words. So here, as we can see, for when the center word is into, we are trying to predict what words can come around it. So it's like we have to find the probability of the word turning, given that the center word is into. And same for the other 3 words as well, problems, banking, and crisis. So this is Skipgram. And here we can see that here we have 2 matrices. One is one matrix is for the word embeddings for context words, and the other one is for center words. So this we discussed briefly last week, so I'll quickly run you through this. So every word when given a sentence like this, problems turning into banking crisis as, we'll pick with one center word and the window could be 2, 5, 8 or anything. So here it's 2, which means we'll be trying to predict 2 words on one side of the center word and the 2 words on the other side as well. So here we can see that problems turning come under context words, and into will be the center word here for this step. So for the next, when we slide the window and go for the next step, into will no longer be the center word, banking will be the center word, and turning and into will be the context words. So this way, every word is going to be a center word as well as a context word too, which is why we have 2 matrices. Here, U matrix contains the word embedding representations for the context word representation. So in the example, that contains the word embeddings for the words problems, turning, banking, and crisis, along with other vocabulary. So likewise, since we also have center words, we have another matrix which contains the word embeddings for all the center word representations. So why are we having 2 representations here? It's because there has to be some kind of differentiation between context words and center word. That way we'll get better semantic representations. Anyway, towards the end, what they're going to do is they're going to take the average of these 2 matrices, and that way we'll end up with one word embedding representation for every word, which somehow merges both the context word representation and the center word representation. So we have the 2 matrices, and for a given step, when we have a center word, we are going to get the dot product, and then we are going to use the softmax and get the probability distribution, which is nothing but the estimated words which the model thinks could probably come in the context of the given center word. So once that is done, so that's how Skipgram works. So one problem here is that probability distribution is going to be very huge, and like the probability distribution is going to be across the entire vocabulary of the data corpus that we have. So which is going to be very huge, but that can be dealt with. We can do much better, which we will be discussing soon. So this is one example of what we get word2vec which is plotted in the 2-dimensional vector space. Normally, as these word embeddings, we can see here that these are 5-dimensional word embeddings. Here the columns represent, each column here represents a dimension or a feature of the words. So here we have 5, but normally they will be like the dimensionality of each word embedding will be 50 or 100, 200, and 300. It could be more, but normally like 200 or 300 is what they normally use for word2vec. So, but since we can only interpret and visualize in 2-dimensional or 3-dimensional at the most, what we're doing here is we use PCA, principal component analysis, which helps us in reducing data which is in some higher dimensions into some lower dimensions. So here what we did is we took the word embeddings here. If you're talking about this, here we have 5-dimensional word embeddings, and that gets converted into 2-dimensional word embeddings. This is just an example. As I said, in an ideal case, the word embeddings will be of dimensionality 100 or more, not 5 or something, because that wouldn't help much. So as we can see here, we get some sort of information from this kind of plots. But the problem is with this sort of representation is that if you see here, we have two words, Samsung and Nokia, and somewhere we have. So the problem with this kind of representation is that when we are reducing the word embeddings from very high dimensionality like 100 to just 2 dimensions, that means that we are going to lose a lot of information. So that can be seen here. Like normally when you have high dimensional vector space, you can visualize much better information. Whereas in this case, some information is lost. And we'll see how Glove can avoid that or improvise on that. So once we have, this is about updating the weights, gradient descent, we all must be familiar with it. It's an algorithm which we have a cost function or a loss function, which gives us an estimate of how far away our model is from the actual predictions. And using gradient descent, we are going to backpropagate the error and update our randomly initialized weights so that in the next step, the model is going to give slightly better results. So this is just the curve of the cost function. It may not be of this sort all the time. What we're going to do is, we can see that initially here, we start with some random initialization. And that is going to give us some cost or some error, to say in general terms. And what we do is we take the negative gradient and try to take tiny steps towards that using learning rate. And that would help us in minimizing the error. So we start with here, theta represents the randomly initialized weights. What we're going to do is once we get the error measure, we're going to multiply that with gradients with the learning rate, and we are going to subtract this value from the randomly initialized values, and then update it and take the updated parameters for the next step. So that is how it works. One thing to add about this is that, as we just discussed, we have a very sparse kind of matrix, because at any point of time, we are dealing with one center word and 4 or 8 or 12 convex words, which means at any point of time, the total number of words are like few. But the update is going to be done on the entire vocabulary, which is kind of, which is not that efficient. So what we can do is, instead of working on the whole data, we only we take one sample data, like in this case, the example that we've seen before. We have to treat this as the data, and whatever we are going to get the error measure, we're going to backpropagate. And then the improvement on that would be like to use minimum a mini batch instead of doing it for one samples. We're going to do it for a batch of samples, like what we have in computer vision. We're going to take a batch of samples like 16 or 32, depending on the GPU that we can afford, and we're going to do that. So this is what I was talking about. We have a very sparse matrix here, so it would be better if we can use a window-sized updates rather than the entire data corpus. So this here, these are all just reviewing some of the things that we discussed. So negative sampling, again, this is another very helpful thing where, if you remember in our previous session from Jay Alamar's blog, we went through negative sampling, where we are going to reduce this problem into binary classification, where we are going to pick 2 words, and the output the model gives is whether those 2 words coexist or not within a given size of the window. So that way we are going to bring down the updates, and the binary classification problem is much easier computation. So for negative sampling, we have to find both positive matches, like words which usually co-occur, and also words which don't co-occur. And also in the lecture, Christopher Manning has mentioned that we have all these frequent words like a and the, which co-occur almost with every other word. So that could be a problem. So what they do is they have some sort of, even in NLP tasks, there is this where all these frequent words are removed and then they are passed to the model. So that is one way of doing it. So it is true that if we take the frequent words like a and the, and we get the dot product of those words with any other words, the chances are that the dot product is going to be higher. That's because from the data corpus, which the models are usually trained on, they usually coexist with a lot of other words. So this is the softmax function. This, again, we discussed all this in the previous session. So the dot product is going to give us how similar these two words are, the center word and the context word, or vice versa. And then we are going to get the probabilities of using softmax. So yeah, and what we see here is the sigmoid function. So we just talked about binary classification. So sigmoid is for binary classes what softmax is for more than two classes. So this, again, what it does is it takes the scores of the dot products, and then it gives out probabilities between 0 and 1, and it does so for two classes. So in our negative sampling case, where the model has to take in two words and output 0 or 1, where 1 indicates that yes, these two words co-occur, and 0 indicates that no, these two words do not co-occur in window of size n. So that's why sigmoid can be used here, since this gives out probability scores just like softmax. So we have two terms here. One is the sigmoid. We are replacing softmax with it here. And yeah, so this is for negative sampling. That's what we discussed just now. And here, if you see here, the 3x4, so when we're doing negative sampling, we have, for a given center word, we need to find both positive words and negative words. Positive words are those which occur along with the center word, and negative words is the opposite. So here, what this does is that when picking when we are randomly selecting the words, this helps in picking words like the model should not always pick the frequent words as the negative words. It should also pick words from it should also pick some rare words, so that way the model generalizes better, get good results. So this helps in doing that. The 3x4 is for that. And so towards the second half of the lecture, Christopher Manning has also talked about some of the previous methods like Cooccurrence Matrix. Cooccurrence Matrix is kind of simple to understand, where you have a matrix X where you have a row, the rows represents the vocabulary, and you're just going to maintain a count of the number of times everybody is going to co-occur with another word. So that would give you a matrix like this. So here we can see that I like enjoying deep learning NLP flying. So let's assume for a while that this is our text data. So we can see that these are the three samples that we have. I like deep learning, I like NLP, enjoy flying. And what we see here, I like, enjoy, deep learning, NLP, flying is nothing but the list of the vocabulary that we have. When we say vocabulary, it is nothing but the list of unique words. So what we're doing here is we are maintaining or having a count of the number of times each word co-occurs with another word. As we can see here, I and like come within the same window twice. We can see here, I like deep learning, I like NLP. So similar, the same goes for I enjoy. I enjoy flying. We can see that I and enjoy are present within window of size 1 only once in our text corpus, which is why we have 1 here. So this way we are going to construct this matrix, and this forms the basis for count-based word embedding methods. And using this matrix, what they're going to do is they are going to apply SVD, which is nothing but, given a matrix X, they're going to factorize that into 3 other matrices. And finally, that is going to help with the final result will be the word embeddings. So the problem with this approach is that every time there is a new vocabulary, this matrix has to be updated, which is not going to be easy when we are talking about real-time NLP applications. And also it is very high dimensional and also sparse. It is very unlikely that all the words in the vocabulary are going to co-occur with every other word. So we are going to have a very sparse matrix, which is not that good. And yeah, so these are some of the problems. So the dimensionality of this approach is going to be huge. Like if you have like 10,000 unique words in your vocabulary, you're going to have a very huge dimensionality for the word embeddings, which is not good. So instead, we can aim for the word embeddings to be of dimensions between 25 to 1,000. That's what we have with word2vec. So this is what the singular value decomposition method. So the X here is nothing but the matrix which we have seen here. It's going to be something like this, the co-occurrence matrix, and that is going to be decomposed into 3 other matrices using SVD technique. There is some math behind it, but you can just think of it as making it simple computationally. Like instead of working on the entire co-occurrence matrix X, which is huge, we are going to decompose that or factorize that into 3 other matrices. That way it's easier to work with. And so there is some math behind it. Maybe we can take that up if we're all interested to discuss more about that. Maybe then we will take it up in one of the future sessions. Or else all you can do is you can use one of the machine learning libraries like scikit-learn or something, which already has functions for this. We can just use those and get the results. So finally, we're going to get for a word, and this will be our matrix X, and then we are going to find SVD. So as we see, we're using NumPy here, and we'll get the 3 matrices that we see here. The 3 factorized matrices here. We're going to get them. And then that will help us in getting the word embeddings, and which can be plotted. So that's one way. And show the lecture notes now.
Question?
Yes, please. Yeah, David.
Yeah. So I pretty much understand all that. What I don't understand is how this ends up translating to a point in 2-dimensional space where 2 words will be close together. What is that a result of? Is that because? Yeah, how's that calculated, or how do we end up with that?
Yeah. So when we're at the time of training and all, where we start with random weights for the word embeddings. Let's say we have 50-dimensional word embeddings, right? And we train the model and we get the word embeddings. And once all of that is done, once we know that, okay, hello?
Yeah, you cut out there for a second, but now you're back.
Oh, sorry. So yeah, so we start with random weights, and we have once using a model, we'll get the proper word embeddings. And once that is done, what we do is using dimensionality reduction techniques like PCA, principal component analysis. That's more like it's a it's a common thing in ML where you use PCA or something like that to reduce high dimensional data into low dimensional data. So what's happening here is that, where is it to plot? Yeah. So normally the word embeddings that we have, they can't be visualized in a plot like this. What we see here is a two-dimensional plot, which represents our word vector space, and all the word embeddings are plotted as a two-dimensional points. But if you're talking about the actual word embeddings, they will be only like of dimensions 50, 100, 200, 300. It's not possible for us to visualize data of that dimensionality.
Right. So it's being sort of boiled down. So what's happening is that because just in an intuition into it, because two words, say sun and moon, are surrounded by similar words in multiple dimensions, they end up being close. Now you could also, if it's words that are surrounded by similar words, but it also sometimes seems to get synonyms, right? Which is a different thing. Sun and moon are not synonyms, but good and very and great or something are very similar. Is there any way to distinguish what's a synonym from what's even an opposite? Like I'm happy, I'm sad. They might have be very close.
Yeah, David. So that's doable. Normally, when you get started with a task like, okay, I want to get the word embeddings for. What you do is you pick some target task. Like if your target task is something like analogies, then what you do is your training data contains something like that. I'll show you the lecture notes and explain this. That would make better sense.
Okay.
Did we get disconnected? Are you still there?
I'm still there. Sorry.
Okay.
I don't mean to, divert your talk. So please, whatever you think is best.
Oh, no, I'm just sharing the notes. Yeah, so do you all see the lecture notes now?
Yes.
Yes.
Okay, good. Yeah, so let me scroll down. Yeah, so if you can see here, we have a list of analogies. Just like we have an example here, Chicago to Illinois. So
I'm sorry.
these are nothing but.
I'm sorry, that's a no. We are seeing your list of files. We're not actually seeing a PowerPoint anymore.
There's a delay, I guess, Avinash.
Okay. I'm really sorry today. There seems to be some problem with my.
I guess we can pull up our lecture notes too.
Yeah, sure. If you can do that, and maybe you can present it, or else, yeah, I'll. Maybe now you can say it. Just see if you can see my lecture notes.
Yeah, I think it's still sharing, but oh yeah, now it's good. Yep.
It's good. You say it. Okay, good. Yeah. So to answer David's question, what we have here is some sort of analogies where we have yeah, David?
Sorry, no, I didn't say anything. I'm just listening.
Okay, yeah. So we have this list here. For the word bad, what the superlative will be worst. Likewise, for big, it is going to be biggest. So this is one sort of like the model. The word, to answer your question, will it just get us related words together, or will it also get other things like synonyms and all? Yes, it can do that. So it can basically do both syntactic and semantic kind of representations. What we have here is syntactic word vector analogies. We can see that just like the word bad is to worst, worst is for the bad word, we have big and biggest. So the embeddings which are properly trained can also get us information like this. So this is one example. And here we see the same for countries as well. Here we have city and the state containing the city. This is another kind of an example. Chicago is to Illinois, and likewise Houston and Texas. So this is another example. So yes, it is not simply going to group or cluster together similar words. It can also derive information like this. Helpful question, David.
Yeah, it does. You cut out there at the end, but mostly I got that. Yes, thank you.
Yeah, you're welcome. So yeah, I don't know whether you got the chance to go through lecture notes or not, but if you didn't, I really recommend you to go through the lecture notes as well, along with lectures and the slides. Like it was basically what all was taught during the lecture. So here we discussed about Cooccurrence Matrix. It's all explained here again. So the main difference between Cooccurrence Matrix and Word2Vec is that they are basically two kinds of methods. The first one, Cooccurrence Matrix, is count-based method, and Word2Vec is more like an iterative method. In Cooccurrence Matrix, what we do is we have this matrix X, which I just showed you, and to get that matrix X, what we're going to do is we have to do one single pass through the entire data corpus, which is kind of huge. Word2Vec kind of methods eliminate that requirement because they don't need the global information. When the information is nothing but the Word2Vec methods or algorithms don't necessarily need to go through the entire data at once before they can start doing anything. That's a very big advantage with Word2Vec. Whereas with Cooccurrence Matrix, before you can get to the word embeddings, you have to do a single pass through the entire data. So yeah, so here it's discussed that there is a problem with cross entropy, which is in cross entropy, we have this denominator or the normalization factor, which is very huge computationally. And to avoid that in GLOVE is nothing but, it's very similar to Word2Vec, global vectors for word representation, that's what it stands for. And it's been done by Stanford team. And it's like they have taken what Word2Vec does, they have improved it, and they have come up with something better. So one of the changes that they did is that instead of using cross entropy, they used another function here, like what we all know, least squares objective. So what it does is it eliminates the normalization factor that we just discussed. So the function is going to be in this form, which is much better than this. So yeah, so let's hoping that the word embedding generation, the process and how it is done made some sense, we have to evaluate how good these word embeddings are. To do that, we have to pick some tasks and we have to test the word embeddings on those tasks. One example is the analogy, which we just discussed. So there are two kinds of evaluation, which is intrinsic evaluation and extrinsic evaluation. So in intrinsic evaluation, what we do is, instead of directly jumping to some real-time task like question answering or conversation making or something like that, we're going to pick some subtask like analogy completion and check how good the word embeddings are on those kind of subtasks. And if we're getting good results, that means that the word embeddings that were generated by the model are decent and good to go. If that's not the case, maybe we have to get some more data or maybe train the model for more number of steps depending on how good or bad the word embeddings are. So this is one way of evaluating, which is intrinsic evaluation. And so, yeah, and another one is extrinsic evaluation. In this thing, what they're going to do is they're going to evaluate the word embeddings or on a more complex system rather than just an analogy finding example. So it could be something like a question answering system, which is much more complex. Yeah, so we can see here that this is just a generalized expression for the analogy. Given that A is to B, we have to find what we can fill in here, what goes with C. So basically what we want to do is xb minus xa. Xb is nothing but the word vector representation for the word B, and xa is the word embedding representation for the word A. We need to we need to find D such that xp minus xa equals xd minus xc. So this is because what we're talking about is not the words themselves, but the vector representations of the words, which are nothing but numbers, which means we can do these sort of subtractions and all these kind of mathematical operations on the word embeddings. So since we are trying to find the analogies, we have to find, this is the equation that we have. So to get that, what we want, so we can find xd by using x minus xa plus xc. So if you remember in our previous study group where we were walking through the blog, we had something like king minus, when you subtract man from king and add woman to that, what you get is queen. So this is nothing but a more generalized expression for that kind of an example. And so when we just saw this 2D plot when we were discussing David's question. So one problem with that is that when you have a word like Nokia, we see that it is close to Samsung. So that way it is telling that, okay, Nokia and Samsung, from the training data that the model has seen, they are grouped together. That totally makes sense because these two are like the phone manufacturing companies, and that makes sense. But let's say what you want is not just that information. You also want some sort of embedding representation, which also captures that in other information like, okay, Nokia is a Finnish company, something of that sort. Actually, all this kind of information do exist in the word embeddings. The only reason we don't see them is because we have brought down the data from something like 100 dimensions to 2 dimensions. And when we do that, it is expected that the word embeddings are going to lose a lot of information. And that is why we are not visually, we're not able to visualize these kind of informations from the 2D plot. If only we can visualize higher dimensionalities, then yes, we might also see relationships like, okay, Nokia is closer to Samsung. It is also closer to other sort of information which convey that Nokia is a Finnish company. So these are some examples. So this is another example where the analogies, the information is not just, it's also contains about tenses. Like when the model can predict that given dancing and danced, it can say that it can give out the word decreased for the word decreasing, which means it also knows some sort of grammar tenses information as well, the syntactic information besides semantic. Is Evan saying something?
So I think someone is not muted. Well, yeah, that's very interesting. Thanks.
Okay, I think he's muted now. Yeah, so those are some of the examples. And here we see how Glove compares with other models. So we have discussed Skipgram, continuous bag of words. So let's concentrate on the second row here, this one. I hope you can see it. So what we have here is that here, the word embeddings are of different dimensions, 100 dimensions, 300 dimensions, and also 1,000 dimensions. And we're going to compare how that is going to change the size of the models and what kind of performance the models provide. So for here, for the Skipgram, when the dimensions are 300, it has about 1 billion, I think it's it's a parameter size, if I'm not wrong. And 61 is what it has given for semantic syntax. So semantics and syntax are nothing but two different kinds of information which the word embedding represent. Here, the tenses contain syntactic information, whereas the previous examples which we were saying, they contain some sort of semantic information. So here, these are comparing results across all these kind of things. So we can see that Glove does pretty well here. Not just, it's like there is huge margin between Glove and the other methods. We see here that Glove for the same dimensions, which is 300, and it is also not that huge. Even the model size is very comparable and almost the same as the other methods. But if you see here, the scores or the performance it has given is very good. Like for semantics, it has reported 80.8, whereas for the other methods have something like 65, 54, 16. And the same goes for syntax as well. There is some plot down saying that would give better information. So this shows that Glove kind of outperforms the other methods. Yeah, so these are some three observations which the authors have concluded, saying that there are several methods that we went through so far. One is Cooccurrence Matrix, which is count-based. We also went through word2vec, and then we quickly discussed Glove as well. These are three different methods, and all of these three try to do the same thing, which is generating word embeddings. So it also depends on the properties of these methods. Like Cooccurrence matrices use count and SVDs for generating the word embeddings, whereas word2vecs are totally trainable end-to-end. These are like different methods which use two different properties and approaches. So the performance or the word embeddings that are generated, it's also dependent on the kind of method that we choose. So we have seen that Glove has done better than the others. And another observation is that the performance of the model is going to increase as the data, the corpus size increases. This, I don't think this needs much explanation. We all know that giving more data is going to help improving the performance of the models. And the third observation is that performance is lower when we have low dimensionality. Like if we are just picking like 5 or 10 as our dimension size for the word embeddings, we are not going to get very good results, or we can be sure that we'll get pretty bad results. So only when we reach to word embeddings of dimensions some 50 or more, we're going to get decent or good word embeddings. Yeah, so this is the plot which it says we have different data sets here. The x-axis represents the results for 5 data sets. We can see that for each of, as we go from one data set to the other, the size has increased. Like here we have 1 billion tokens, whereas here we have 1.6 billion. So it keeps on growing until 42 billions, and we see that every time we get some sort of improvements in the performances. So this is another performance report where we see that what we have here on x-axis are dimensions. Here we have dimensions of the order 100, 200, 300 in the leftmost plot. In the middle, we have window size, and the last two are for window size. So we see that as the vector dimensions size increases, the accuracy also increases up to a certain point. But beyond that, we see that we have some sort of very flat plot here. So like even Word2Vec and all, even I read somewhere that Google has used word embeddings of dimension size 300. So beyond that, they have seen that there is not much difference or improvement in the performance. Yeah, so we discussed like some of the ways of evaluating the word embeddings. Another way of doing that is comparing the results of our word embeddings with that of what humans have done. So what we do here is we check. There are already data where humans have evaluated some of the data and produced some outputs, and we are going to use our model or the word embeddings on the same data, and we are going to get the results. And then we are going to compare the word embedding generated results with that of human evaluated results, and we're going to conclude how good or bad the word embeddings are. So dealing with ambiguity. So this is something that we discussed some time back, like what do we do when a word has multiple senses? Like the word run, here it says that, here is an example where run is both a noun and a verb, and it could be interpreted differently depending on the context. So how are we going to do that? So what we're going to do here is, in Glove, what they have done is they use some sort of clusters where, so for a given word, we're going to get the context window, like 5, if the window size is 5, we're going to get all the words, 5 words before the current word and 5 words after the current word. So we'll be words on the current word. So, and then what they're going to do is they're going to find some sort of k-means to cluster these representations. That way, the word, maybe then, going back to a previous example, Nokia is going to form a cluster with words like Samsung, Motorola, and those sort of words. And also it is going to form another cluster with another group of words, which it is semantically similar to. I hope that made sense. So that way we are going to get word embeddings which contain more information. Yeah, so these are some other examples. So any questions so far, or is there anything anyone wants to add?
Hi, this is Christine. I had one quick question for you. Can you hear me?
Christina, go on.
So when he talked
yes,
about,
I can hear you.
When he talked about the multiple meanings of certain words, he sort of showed the Jaguar example and how it shows up in different parts of the printout. And he talked about renaming it so that there are different instances of that word. And I'm just wondering, how do we store that information? How do we store the fact that we have now changed one word into 5 different words based on the meaning? Does that question make sense?
Yeah, I remember that discussion from the lecture. And if I remember it right, I don't think he discussed about that in detail, or did he? He just mentioned that using glove, they're going to form some sort of clusters. That way you get multiple senses for the same word using these clusters. Am I right? You're referring to that part of the lecture, right?
Yes, that's right.
Yeah, so this is exactly for that. So how do they, but the relabeling thing we can see here, like each word occurrence is relabeled to its associated cluster. So maybe I'm not sure about that part as of now, but I'll look into that. Maybe I can get an answer for that. If anyone wants to take that up, please add something if you have. So for those of you who didn't get a chance to go through this part of the lecture, Christina's question is that we just discussed in some cases words will have multiple meanings depending on the context in which they're used, like Nokia, or as Christina said, the word Jaguar. So depending on the situation, the word might be used for different purposes. So how are we going to embed that information in our word embeddings? So if I remember it right from the lecture, word2vec can't do it, but glove does it with the help of some sort of clusterings. As it just said, it is going to form clusters. Like for the same word will be close to not only one word or one group of words, but to several groups of words. That way, the vector space is going to contain information for multiple purposes. I'm not sure whether that is clear or not.
I think so. I think what I was wondering was, so that when we reuse this corpus, do we now have 5 different instantiations of this word Jaguar, or is it just still that one word and we somehow know it has 5 different meanings? But I can keep reading the notes and see if I can find more about that.
Sure. I don't remember, like they just mentioned here that some sort of relabeling is done, but besides that, I don't really think they talk much about it in the notes. But yeah, please let us know if you get to know more about it.
I would imagine it would be that you couldn't really modify the original corpus, could you? I mean, I guess you could, but I would imagine that it's saved. Yeah, I mean, this doesn't answer the question, but it must be saved somewhere else.
Avinash, just to
Like
kind of go back. Sorry, go ahead. Dude.
No, go ahead. Go ahead.
Now, I'm not sure, but from what Avinash you already told, like answering Christine's question about Jaguar 1, Jaguar 2, Jaguar 3, is that more of a visualization problem? That's why we're kind of trying to cluster. Whereas the original Jaguar in whatever 100 or 50 dimensional space actually is near to both Samsung as well as Finland. So I'm not sure about what this paper exactly deals with, the k-means clustering part of it. Yeah. I feel that is more of a representation issue. So the actual embedding actually holds.
Okay, so I remember that in the lecture, he makes the point that when we reduce the dimensions from, let's say, 100 dimensions to 2 dimensions, there's a chance that this kind of information might get lost. Like just exactly what you said, like it's there in the representation, but when you're bringing it down to 2 dimensions and when you're trying to visualize that, you may not see these kind of representations in the word embeddings. Am I right?
That's right. Right.
Yeah. So, but they seem to add this, like to handle ambiguity, this k-means thing. So I don't know whether it's common for both Word2Vec and Glove, or is it something which they have added to Glove alone? I'm not sure about that part. So do you think Word2Vec handles, like going back to the Jaguar example, so if we have the original word embeddings with 100 dimensions, it is going to contain information about the other relationships as well, not just one group of synonyms or the words which it is similar to.
Yeah, that's what I think. I imagine. I'm also not very sure.
Okay, sure. Maybe we can look into that, and if anyone finds an answer, maybe we can post that in the channel.
Abhinav, can I help answer Christine's question?
Yes, please, Mahesh, go ahead.
No, intuitively I have not seen the videos, but what I can guess is that the embeddings itself for the word Jaguar will adjust to the different situations in which the word Jaguar is used. Okay, so you will not have different representations of Jaguar. You would probably have only one vector of the embedding of Jaguar, but it will adjust, the numbers itself in that embedding will adjust accordingly. This is my intuitive answer to Christine's question.
Okay, so maybe we could experiment with that analogy function and sort of try different analogies that are representative of the different meanings of Jaguar, just to see if it gives us a different answer, even though we're using that same word. That might be a neat way to explore that.
Yeah, because see what's happening is that the text corpus has got Jaguar, which is being represented in different meanings. So the algorithm itself will adjust the embeddings accordingly. So you would not have multiple representations of multiple instantiations of the same word. The embeddings itself will adjust. Is my intuitive answer.
Yeah, there may not be like different representations for different contexts or scenarios, but as Prashant was saying, this could be just to handle the visualization constraint of not being able to look beyond 2D or 3D. So
Actually, sorry, just kind of looking at the paper, and the abstract says accounts for polysemy by learning multiple embeddings per word. So I think, yeah, probably next session we should kind of go through the paper and then discuss.
So if you can see here, there's a paper which is referred here, Improving Word Representations by a Global Context. So maybe going through this paper would answer all these questions, I believe. It would at least tell us whether these improvements are for the word representations or just for the visualization. It could be for representations, yeah. Anything else that anybody wants to say or add to this?
See, on the visualization part, I will say, that's a separate technique. You're just trying to create a graphical representation of your embedding. So I personally believe visualization should be kept separate. As far as the embeddings are concerned, how the embeddings are getting generated, the numbers which are getting generated is really reflective of your corpus, and how the words are getting represented in the corpus, and how the algorithm is learning the same. So ultimately it will boil down to because if you see the closeness of the words, let's say man word is close to the word let's say doctor, or let's say, so this closeness itself represents the meaning which the algorithm has found from the corpus of the hundreds of millions or thousands of words in the sentences that it has learned. So And the visualization part is completely different because, when you have a 300 dimension vector, which you are trying to visualize maybe in 2 or 3 dimensions, the technique of visualization, I think, has to be looked at separately.
Yeah, I would like to add something here. So as Mahesh was saying, that when we have a vector, when we have a word which is the meaning is ambiguous or maybe has multiple meanings. So like the word jaguar, it might be close to an maybe cats in one dimension, but it could be close to another, maybe Bentley in another dimension. So in exercise 1, if you do this, what do you call multiple meaning words? I'm forgetting the term for that. So when you get the vector of the probabilities, so for suppose you put it for jaguar, so it might say it might give you something related to car having the highest probability, but second thing might be very much related to a cat. So in that way, so the word representation is what I think is word representation is same, but the thing is because we have multiple a very large number of dimensions, it can be very close to different kind of meanings and different kind of words in different dimensions. Obviously, it can be captured in visually because we are only dealing with 2 to 3 dimensions. So that's my take on that.
Yeah, I think it's right. I think what you're saying makes sense.
Yeah, thanks, Mahesh and Vikas. Yeah,
Thanks.
so maybe we can go to this paper and hopefully that would clear all these doubts. And if anyone's anything or goes through anything related to this, please post it in the channel so that we can also go through those things. Yeah, so we already crossed the time. So yeah, so is there anything else that
yeah, I was just going to ask, this document that you're showing now, is that available for download?
Yeah, David, you just have to go to CS224 course page. For every lecture, almost for all the lectures, they have lecture notes. You can download it right from the course webpage. It's available there, next to slides. It will be available right next to slides. Yeah. So anything else that you guys want to discuss in this session? We still have a few things left in the lecture notes. So if there's
just
nothing,
a question.
then yeah, Rahim.
This is more so for actually I have 2 questions. I'll ask the logistics kind of question first. Are we going to go through the assignment next week then?
Yeah, sure. We can do that. I actually thought of doing it today, but we already, I think we took much time for this. Okay. Yeah, so we can take up the assignment next week. Sure. Yeah, I started to work on that. Like I almost finished it. So yeah, we can do it next week.
Okay, yeah, that would be great.
Is there anyone, yeah, sure. Is there anyone else who wants to like present the assignments? So this even in the future study groups, if anyone wants to host or take up any of the lectures or assignments, then please feel to update your name against your interested lectures in the plan sheet. It's available in the study in our channel. You can find it. So yeah, we'll surely do the assignment next week. Yeah, and if anyone's interested to do it next week, please let me know so that we can plan accordingly.
Okay, great. I had another question, which was, it was kind of like it came up a couple of times in the lecture notes, so I thought to ask. So it's about TF-IDF.
Oh yeah.
Why, like, usually, I mean, my perception of it was, and maybe you could like explain what it is when you answer for anyone who doesn't know what it is. But my understanding of it was that it's a better version of word Cooccurrence matrices. So then in that case, why is it not used for glove, or why have they not even mentioned it for singular value decomposition?
Yeah, so I don't think I can answer that because I remember about it. I didn't check it anytime recently. But one of the reasons I think could be that, again, TF-IDF is going to be like one of the problems that we discussed with Word and document co-occurrence matrix is that you have in those kind of count-based methods, you start with global information. Like if you have a text corpus with 1 million examples and something like that, and like millions of words of vocabulary, you start with creating this huge matrix first. That's the first task that you're going to do. So which means this method needs global information, the entire data. And that's one of the drawbacks which Word2Vec try to address. And they go for the iterative based approach rather than the count based approach. So this is one thing that I think right now, based on what I know about co-occurrence matrices. But yeah, if anyone wants to say something about TF-IDF.
Yeah, I think TF-IDF is very primitive compared to what this algorithm is doing. Because TF-IDF, what I understand is it is just looks at the the frequency of the word which has been used in the document. And whereas here, what are we doing? Here we are looking basically at every word, and we are trying to see what is the probability of the words which are surrounding this particular word, and we are doing it for the entire corpus. We are doing it word by word, sentence by sentence, paragraph by paragraph. Whereas in TF-IDF, you just have a numerator and you have a denominator. You don't look at anything else. I had read about TF-IDF long time back, but I think these techniques are far more advanced. This is my suggestion, my opinion.
Right, yeah, I get that. Yeah, no, I 100% agree that there are better techniques, but for glove, you start with the Cooccurrence matrix, right? So if you're starting with these large sparse matrices anyways, why isn't TF-IDF used? Because like one drawback of like word Cooccurrence matrices is that it's sparse and it doesn't, it may be stuck within a certain document, as in, like, what I mean by that is it doesn't, it may give higher priority for like the stop words and the common words that are used.
Yeah, no, see, TF-IDF is essentially looking at the relationship of a term with respect to the entire corpus. Whereas when we look at any of these other algorithms, whether it is Skipgram or whether it is CBAW, we are looking at the relationship of every word with respect to each other. Whether you approach it from inside out, which is the Skipgram approach, or whether you approach it from the outside in, which is the CBAW approach. So so we are doing far more complicated things, because finally, see, when we are creating a matrix, or when we are creating the probabilities of how close are these two words likely to come to each other, how far they are. We are computing the distance of every word to each and every word which is there in the corpus. Whereas TF-IDF is a very, very simple matrix. So I think we are talking of two different things over here.
Okay, all right. I mean, I still do have a few questions, so then I can take this. I don't want to take up too much time on it. But yeah, thanks for your thoughts.
Yeah, but that's a good question, right? Maybe we can take this up as well along with the previous thing about word representations, and we'll see if anyone. I mean, I'll go through these things and I'll see if I can find the answer.
Okay,
All right,
thanks.
thank you.
Yeah, thanks. So, any other questions or anything else that anyone wants to say?
Just thank you.
Sure.
Yeah, thanks so
David.
much.
Thanks,
Thanks, Avinash.
Abhinav. Thanks for your time.
Any
Thanks,
questions
everyone.
Thanks, Avinash.
about the FastAI NLP course? Do you know what Sanyam was going to host? Do you have any updates on that?
Yeah, I think he's going to do it tomorrow, right? I think I'm not sure whether it's confirmed or not. I think he was.
Okay.
Yeah, I think it is confirmed, and it's going to be.
You broke up, Jed. Are you there?
Yeah, I was wondering if it's my internet or.
Oh, no, I can hear it.
Okay. Jess, we lost you.
While we're waiting for her to come back, is there a lot of overlap, do you know, between that one and this one?
I personally didn't go through those lectures yet, David. I think that again is going to be more practical kind of a course, like how FastAI usually is. And this, as we see, is more like both. I mean, it's more like building things from ground up, understanding all these methods, and then getting into things like recurrent neural networks and all those things. We're not yet there. So yeah, these two are like very different in terms of the approach.
Yeah. Okay. Cool.
So for now, I'm thinking I will attend the other study group on FastAI NLP, just to understand things and what is being covered in FastAI NLP. But I'm going to primarily focus on this because I don't want to like go over multiple things at the same time. I think they're going to start from tomorrow, Sunday. But I think he was also checking what time and all. So I'm not really sure whether it's confirmed or not. We can check. We can check with Sanyam about it.
Sounds good. Thanks, Avinash.
Thanks, Prashant. So I will update the plan sheet next week. For the study group, we'll be having week 1 assignment. So if anyone gets the time, please go through the assignment. And if you want to share or if you want to add anything to the assignment when we discuss it next week, please feel free. And if there is nothing else to discuss, I think we can end today's study group. So yeah, thanks all for being here today and have a happy weekend.
Thanks. See you next week.
Thank you.